Hello and welcome back. This is the part 2 of mathematics required for competitive programming. In case anyone hasn't watched part 1, where modulus operation was discussed and its property was also discussed, in because that will be useful in this part of the lecture. And in this lecture, the main focus is to figure out the GCD of two positive numbers, which will be worked out using Euclid's algorithm. And here both version will be discussed, slower and the faster version. So let us say that Euclid's algorithm states that to figure out the GCD of two positive number, for that A has to be greater than B, and A can be represented like A is equivalent of saying B times Q, where Q is the quotient and R is the remainder. Then GCD of two numbers or between a pair of numbers A and B is equivalent of saying GCD of B and A minus B. This is the idea given by the Euclid. And what is GCD of a single number? Let's say GCD for 15 has to be figured out. You will factorize this 15 into divisors, which will be 1, 3, 5 and 15. But the highest factor which divides both for GCD for a single number can be computed? No. Now, let us understand the Euclid's algorithm working through an example where one can say that A is, let's say, 28, B is 13, and this can be represented like Q, A, B and R, where Q is the quotient obtained on dividing the number. So here 28 and B is 13. 28 on dividing 13, it will be by 1 time, 2 times 26, and remainder is 2. Now here A will become the value of B and B will take the value of R. This is basically this step. At this step, A will now take the value of B, which is 13, and B will take the value of remainder, which is given by A minus B. So GCD for this number is still not obtained. It will be obtained unless A becomes less than B, or B or any of the number is 0. Either this condition is hold, or A is 0 or B is 0. Or if this big condition holds and this condition holds, then one can figure out the GCD value. Now this will be carried for 6 times, remainder is 1. Again do the following 2, 1, and it will be carried for 2 times, remainder is 0. Then this can be 1, 0. So any number, and it is said that it is positive number, so 0 is not considered a positive number here. Hence the GCD value, the obtained value of A is the GCD. So GCD for 28, 13 is 1. And the value of GCD equal to 1 are saying that 28 and 13 are co-prime. 4 prime numbers. Here is the faster version of Euclid's algorithm, and if look carefully, that GCD of B and A minus B, where A minus B can be represented like A minus of A by B floor times B, and this idea was discussed in the modulus operation, which is figuring out the remainder value. So this is saying like A mod of B. Hence, GCD can be represented as A if the value of B is 0, or in case value of B is not 0, then GCD can be B and A mod of B. This is the recursive approach of getting the GCD value, and also it's a faster approach to figure out the GCD value. Consider the same example of A having the value of 28 and B having the value of 13. So GCD of this number 28, 13 will be given like GCD of 13, A mod of B, which is 28 mod of B, which is 2. So this can be basically 1, or in case if further operation has to be carried out, then GCD of 13, 2 is saying like 2, of 13 mod of 2, which is 1, and then this can be computed like 13, so this will be 1, of 1 mod 2, 2 mod 1, which is 0, and the value here becomes, and then A will be returned, which will be 1. Now how many steps this has worked out? 1 step, 2 step, and 3 step. Total 3 times computation has been carried out to get the result. Whereas the slower version, how many times the computation has taken place? Here the computation has taken place 1 time, 2 times, 3 times, 4 times. So here 4 times computation has taken place to compute the GCD value. Here only 3 times computation has taken place, but for the smaller number it doesn't make a difference. Time complexity of figuring out the GCD value using Euclid's algorithm is given as, or is big O of log of mean of A, B. And to understand why this is the case, let us represent this value GCD of A, B. So in first operation or first step, this is the case A mod of B. This is first step. In the second step or second operation, GCD of, so this value will become the B, A mod of B, and using this value of B, this can be computed like A mod of B. And again this can be simplified as or this can be worked out like GCD of A mod of B followed by, now this becomes B, so A mod of B. That is how it will keep on continuing until GCD of this will keep on continuing until GCD of A comma 0 is reached, which will return 1. So this will be performed in one operation. And to compute the depth of this recursion, this is the depth, like it will be mean of the number of times it will be performed is mean times A of B. That will be the depth of the recursion, and every time we can see that it is being divided in two halves, like first is A, B, then B is being swapped, so here A is being swapped with B, but B is getting A mod B. So this operation is performed twice on every instances. So this just basically becomes, hence we get the time complexity order of log of mean of A. That is for the Euclid's algorithm, faster and slower. In slower than also, only time that is being taken is in the subtraction phase. Every time it needs to perform subtraction, so that will give us the time complexity of order of mean of AB. So that many times subtraction to be performed, and hence it becomes much slower than the performing modulus operation. Hope you enjoyed the analysis and have gained some knowledge about the Euclid's algorithm. In case of query, kindly post in the comment box. Thanks for watching.